Welcome to the new section of this course, STL Algorithm Basics. Now let's move on to the video, Operations on Containers. Let's start with copying items from containers to other containers. Here, we will use different variants of copy. Let's understand our code. First, include all headers we need for the data structures we use. Additionally, we declare that we use the standard namespace. We will use pairs of integer and string values. In order to nicely print them, we should first overload the stream operator for them. In the main function, we fill a vector of integer string pairs with some default values. And we declare a map variable which associates integer values with string values. Now we use standard copy n to copy exactly 3 integer string pairs from the front of the vector to the map. Because vectors and maps are completely different data structures, we need to transform the items from the vector using the insert iterator adapter. The inserter function produces such an adapter for us. Please be always aware that using algorithms like copy n combined with insert iterators is the most generic way to copy insert items to other data structures, but not the fastest. Using the data structure specific member functions for inserting items is usually the most efficient way. Let's print what's in the map afterward. We have often been printing a container's content using the standard copy function. The standard OStream iterator helps a lot in that regard because it allows us to treat the user shell standard output as another container we can copy data into. Let's clear the map again for the next experiment. This time we move items from the vector to the map, and this time it's all the items. We print the new content of the map again. Moreover, as standard move is an algorithm that also alters the data source, we will print the source vector too. This way we can see what happened to it when it acted as a move source. Now let's compile and run the program and see what it says. Go to the terminal, type in the command for compiling the code. After the successful compilation, let's execute it. Cool! This is the result. The first 2 lines are simple. They reflect what the map contained after applying the copy n and move algorithms. From the code, this line is used for copying, and this for moving. The third line is interesting because it shows that the strings in the vector that were used as move source are now empty. This is because the content of the strings has not been copied, but efficiently moved, which means that the map uses the string data in heap memory that was previously referenced by the string objects in the vector. We should usually not access items that were a move source before we reassigned them, but let's ignore that for the sake of this experiment. Next, we will move on to sorting containers. Let's take a look at the code example. So go to the Atom editor, then click on the ex2 directory, and inside that, click on the sortingcontainer.cpp file. This is the entire code. Here we are going to play with standard sort and standard partial sort. So let's understand this code in detail. First, we include all that's necessary and declare that we use the standard namespace. In this function, we will print the state of a vector of integers multiple times. So let's abbreviate this task by defining a small procedure. In the main function, we begin with a vector that contains some example numbers. Because we will shuffle the vector multiple times in order to play with different sort functions, we need a random number generator. This isSorted function tells us if the content of a container is sorted. This line should print 1. With shuffle function, we shake around the content of the vector in order to sort it again later. The first 2 arguments denote the range that will be shuffled, and the third argument is the random number generator. Here, the isSorted function should now return false, so that 0 is printed, and the values in the vector should be the same but in a different order. We will see after we have printed both again to the shell. Now we re-establish the original item ordering by using standard sort. The same prints to the terminal should now again give us the sorted ordering from the beginning. Another interesting function is standard partition. Maybe we do not fully sort the list because it is sufficient to just have the items that are smaller than some value at the front. So let's partition the vector in order to move all the items that are smaller than 5 to the front and print it. The next sort-related function is partial sort. We can use it to sort the content of a container, but only to some extent. It will put the n smallest of all vector elements in the first half of the vector in a sorted order. The rest will reside in the second half, which will not be sorted. What if we want to sort a data structure that has no comparison operator? For that, let's define a structure and then make a vector of such items. The sort function optionally accepts a comparison function as its third argument. Let's use that and provide it with such a function. Just to show that this is possible, we compare them by their second field b. This way, they will appear in the order of myStruct: b and not myStruct: a. The last step is printing the sorted vector of myStruct items. So now let's compile and run our program. Go to your terminal, navigate to the directory ex2. Next we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. Nice! Here is the output. The first one results from the standard isSorted call after initializing the sorted vector. Then we shuffled the vector and got a 0 from the second isSorted call. The third line shows all the vector items after the shuffling. The next one is the result of the isSorted call after sorting it again with the sort function. Then we shuffled the whole vector again and partitioned it using standard partition. We can see that all the items that are less than 5 are also to the left of 5 in the vector. All items that are greater than 5 are to its right. The second to last line shows the result of standard partial sort. All items up to the middle appear strictly sorted, but the rest are not. In the last line, we can see our vector of myStruct instances. They are strictly sorted by their second member values. Next, we will be removing specific items from containers. Let's see the practical code example for the same. Go to the Atom editor, open the ex3 directory, and inside that, open the respective .cpp file. I have highlighted the entire code for you. Just have a look at it. We will transform a vector's content by removing items in different ways. So now it's time to understand the code. Let's import all the needed headers and declare that we use the standard namespace. A short print helper function will print our vector. In the main function, we'll begin with an example vector containing some simple integer values. We'll also print it, so we can see how it changes with the function we apply to it later. Now let's remove all the items with the value 2 from the vector. Remove function moves the other items in a way that the one value 2 we actually have in the vector vanishes. Because the vector's actual content is shorter after removing items, remove returns us an iterator pointing to the new end. The items between the new end iterator and the old end iterator are to be considered garbage, so we tell the vector to erase them. We surround the two removal lines with a new scope because the new end iterator is invalidated afterward anyway, so it can go out of scope immediately. Now let's remove all the odd numbers. In order to do so, we implement a predicate, which tells us if a number is odd, and feed it into the standard removeIf function, which accepts such predicates. The next algorithm we try out is standard replace. We use it to overwrite all values of 4 with the value 1, 2, 3. The replace function also exists as standard replace if, which also accepts predicate functions. Let's pump completely new values into the vector and create 2 new empty vectors in order to do another experiment with those. Then we implement a predicate for odd numbers again, and another predicate function which tells the opposite if a number is even. The next 2 lines do exactly the same thing. They copy even values to the vectors v2 and v3. The first line does this with the remove copy if algorithm, which copies everything from a source container to another container which does not fulfill the predicate constraint. The other line uses standard copy if, which copies everything that does fulfill the predicate constraint. Printing both the vectors should now result in the same output. So it's time to compile and execute the code and check the output we get. Go to your terminal, navigate to the directory ex3. Next we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. we obtain the required output. The first output line shows the vector after its initialization. The second line shows it after removing all the values of 2. The next line shows the result of removing all the odd numbers. Before the fourth line, we replaced all the values of 4 with 1, 2, 3. The last two lines show vectors v2 and v3. Following that, we will move on to the last topic, transforming the contents of containers. Go to the Atom editor, click on the ex4 directory, then open the respective .cpp file. This is the entire code that we will be looking at in detail. Here we are going to use standard transform in order to modify the items of a vector while copying them. So let's understand this code in detail. As always, we first need to include all the necessary headers, and to spare us some typing, we declare that we use the standard namespace. In the main function, we have a vector with some simple integers that will do the job as an example source data structure. Now we copy all the items to an OStream iterator adapter in order to print them. The transform function accepts a function object which accepts items of the container's payload type and transforms them during each copy operation. In this case, transform function accepts function in which we calculate the square of each number item, so the code will print the squares of the items in the vector without us having to store them anywhere. Let's do another transformation. From the number 3, for example, we could generate a nicely readable string such as 3 raised to 2 equals 9. Here you can see this int2string function object does just that using the string stream object. Here we have declared then a string stream object. And in this part of the code, the transform process is done. The function we just implemented returns us string values from integer values. We could also say it maps from integers to strings. Using this transform function, we can copy all such mappings from the integer vector into a string vector. After printing those, we're done. Now let's compile and run the program. Go to your terminal, navigate to the directory ex4. Next, we will clear the screen using the reset command. After that, type in the command for compiling the code. After the successful compilation, let's execute it. Excellent! We obtain the required output. Here you can see we have printed the squares of the number. For example, 1 square is 1, 2 square is 4, 3 square is 9, and so on. So we have successfully printed the square of the number. So here we have come to the end of this video.